So yeah, thank you for organizers for inviting me. It's a pleasure to be here, and thank you for coming to the one talk. So I'll try to make it good. So today I'll talk about increasing a sequence of dimension S to a sequence of dimension T with few changes. This is joint work with Noam and Joe and Sasha Shen. All right, so some of you have seen some presentations on this before, like sometime like late last year. There was some open question, so this will answer that. But first I'll do some background on kind of how this sort of direction of questions got going. So there's this observation that's been known to everybody for a long time, is what's a nice way to make a sequence of effective dimension 1 that's not random? Well, just start out with a Martin-Loaf random and mess it up on a density 0 of points to get a sequence of effective dimension 1. And then a question was going around, and I knew of it because Rod kept asking us, though I guess I don't know whether it originated with you or not, but there's this question of whether you can make every sequence of effective dimension 1 by taking a random and messing it up on a sequence of density 0. And so the first theorem that we proved was that that is the case. So the sequences of effective dimension 1 are exactly the sequences that differ from a Martin-Loaf random on a set of density 0. And the sort of method that we used to prove that turned out to be useful for some other questions that are related. Yes?
But observation is more that whenever you take a random split that you always take dimension 1. The formulation is a little bit puffing.
I agree with what you said, and maybe I could have put a better wording on this slide, but that's exactly what I meant to say.
Because random always have dimension 1.
Say again?
Always have dimension 1.
Yes.
So you don't have to make them in dimension 1. Yeah.
Yes.
But you cannot avoid to make them.
Yes, I should have said you can make sequences of effective dimension 1 that are not random by flipping density 0 bits on a random in some way that you can recover some information from them. Okay, so another observation kind of related to the first one. Let's say that you have a random and you want to use it in order to make a sequence that has effective dimension 1/2. Well, one way that you could do that is just like whatever the random has on all of the odd bits, change them all to 0, and like leave the even bits remaining as they are. So you'll only have to change half of the odd bits, because half of the odd bits already had 0 anyway. So with density 1/4 of changes, you can turn a sequence of effective dimension 1 into a sequence of effective dimension 1/2. So then you could also ask, okay, well, is that the best that we can do? Like what density of bits actually do we need to change on a random in order to get it down to effective dimension 1/2? So there's kind of a naive bound on the distance that you could need. And this naive bound just comes from a coding argument. So let's say that you've got two reals, x and y, where they differ from each other on density d. So here I'm using this upper density in case the limit of the symmetric difference between x and y does not exist. Then we'll just say whatever the lim sup of that symmetric difference is will be the distance between those two reals, x and y. So if two reals have some distance between them, well, then you can use one of them to code what's going on in the other one pretty easily by, for any initial segment of x that you want to describe, first describe an initial segment of y, and then describe the changes that you made. Okay, so this h is Shannon's binary entropy function, which translates between density of bits and density of information that you can encode using those bits. And because I'm going to get into some kind of convexity arguments, I know we all know what this function looks like, but I'm going to draw it so I can point to it. Later. So here's graph of that binary entropy function, h. Okay, so with density 1/2 of bits, you can get fully random sequences. And with some smaller density of bits, there's some limit on the amount of information that you can encode in those sequences. In particular, if you are going to encode like a set of density D, then because h of D is the most like information that you could encode into that dense set, that's also enough bits of information to say, okay, here's where the changes were. Right, so you can say, all right, I want to encode some initial segment of X, so I'll just describe an initial segment of Y, and then with some small number of bits, I'll describe where are the changes in order to get to X, and that gives me a description of an initial segment of X. So this is like a very naive bound on on the distance that would be needed. Because, for example, if we start out with X that is random, so has like effective dimension 1, and we want to get down to Y that has some small dimension, so some small dimension S, then we're going to need to make D at least like big enough so that S plus h of D is greater than 1. Like, otherwise, it just won't work. So that gives a naive bound in the case that we start out with a random and want to decrease to dimension S, that we're going to need to use at least this distance. And in general, and this distance is, gives us a better bound than so on the previous slide, we started with dimension 1 and dropped to dimension 1/2 using density 1/4 of bits, so like 25%. But using this function, you can actually do it with some like 10% of changes. All right, so 10% of changes would be like sort of an absolute minimum of what you could possibly need based on this naive bound. But it turns out also that you can go in the other direction and say, okay, 10% actually will be enough changes to a dimension 1 real in order to get it down to dimension 1/2. Okay, so before I show the proof of that, which is a short one, just want to go some notation that I'm going to be using throughout the talk. So throughout, so all of the constructions are going to be kind of in some sense like initial segment constructions, and they'll always sort of go at a certain speed. So whenever I have any real X or any real Y, I'm going to think of them as a concatenation of a bunch of strings. And the strings are getting longer over time, but sort of at this like specific I² rate. So this is going to turn out to be some kind of like Goldilocks rate where it's fast enough that some things work and slow enough that some other things work, and everything's going to work. All right, so by the dimension of a finite string, I just mean its complexity divided by its length. And then in the context of some X that has these sigma as written here, I'm always going to use the letter S sub I to refer to the dimension of the ith chunk relative to all of the chunks that came before it. So the reason that this is kind of an important quantity to keep track of is that you can actually use it to approximate the dimension of initial segments of a real. Yes, Rupert?
Sorry, conditional dimension is just you use the K, which is conditional. Or...
Yes.
Okay.
Yes. So if you take all of these conditional dimensions and take their weighted average according to, just weighted according to the length of the segment that each conditional dimension comes from, then that weighted average of conditional dimensions actually gives a pretty good approximation to the dimension of the string itself. So that follows from the symmetry of information facts about Kolmogorov complexity, but it depends on this growing fast enough and slow enough as well. So there's some like approximation thing going on. But for the purposes of this talk, for where I want to get to, it's right to think of it like this. It won't lead you astray. And then, of course, if you also want to look at density of bits in initial segments, well then that averaging formula actually just gives you the density like straight up. Right? So if I want to know what's this is sort of a trivial identity. It's sort of like written too big somehow. But we want to notice that kind of both of these properties of initial segments, both their dimension and their density, can be either well approximated or just straight up obtained by taking an appropriately weighted convex combination of the conditional densities or just, conditional dimensions and densities, respectively, of those individual chunks. All right. I think that everything that I will do next will be completely boring if like any part of this is unclear, and maybe kind of fun if this is clear. So definitely like tell me right now if I'm like not making sense about what's going on so far. All right, awesome. Okay, so let's now look at proving that second theorem. So there are a bunch of facts about finite strings and like how you can change finite strings on various density of their bits and end up with strings that have different finite dimensions. And so one of those facts is for a finite string, gives you a bound on how much you have to change a string in order to lower its dimension to less than s. So you kind of maybe want to think of this sigma as being some string that is a random finite string. Then for any s that you want to reduce its information down to, you can always find some some neighbor that lives within this distance. Remember, this is the distance that came from the naive bound, such that that neighbor really does have a small complexity. So this is a finite fact, but it's actually the result that we want for the infinite case. So in this very first example, so there's going to be two preparation examples, and then we're going to talk about increasing dimension s to dimension t. But in this first example, it's very easy to do, because if you just start out with x considered as this concatenation of chunks, then you can produce a y that's within the specified distance by following a very simple strategy of just, for each one of the sigma, apply this fact, find some tau where that tau has dimension less than s and is within this distance of sigma, and then just like put that tau, and then just like concatenate them together. Right, so I'm even just making like the dimension of tau like just straight up less than s, like not even conditional dimension, but then the conditional dimension will be less than s as well. All right, so just take all these strings, just replace each one of them, and then you end up with a y that has the property, well, every one of these chunks has dimension less than s, so conditional dimension less than s. So when you average them, y has effective dimension less than or equal to s. And also, each one of the density of difference between these chunks. So the density of difference between this chunk is less than that number, also for the second chunk, also for the third, and so on. So again, taking the appropriately weighted average of the same number every time, you get that y, that the symmetric difference between x and y is also going to be bounded by this. So, okay, so this is the easiest case. All right, so let's now look at another direction. So let's say that instead of starting with a random real and decreasing down to effective dimension s, I want to start out with some real effective dimension s and increase it so that it has effective dimension 1. All right, and then if I want to make it a random, then by the first theorem, I can just change it on a further density 0 of bits and get to random. But at this point, let's just talk about effective dimension. You can make the following observation. So, okay, so consider a Bernoulli p random. All right, so take some coin that has probability p of coming up heads and flip it a lot of times, and get the sequence that comes out. That sequence is going to have density p, right? Because your coin comes up heads probability p of the time. So, if you look at this translation that you have between density and dimension that's given by the Shannon entropy function, then, okay, so whatever P is, so maybe you've got some P here, you can get some, probably relatively larger effective dimension, like for that real. So like, for example, if P is like approximately equal to 0.01, then you can get h of P all the way up to a half. So just with, Bernoulli 10% random, you can get effective dimension 1/2. And if you want to turn that particular string into a string that has effective dimension 1, then just purely for density reasons, you're going to have to use at least 1/2 minus P density of changes. Because until you use that density of changes, the density of your real is going to be wrong. Right? You started out with just a 10% density. If you want to get to effective dimension 1, then you're going to need 1/2 density. So you're going to need to make at least density 1/2 minus P of changes. That's like unavoidable. So, okay, so that's an observation. So now you could ask, okay, like this sort of like worst case situation. So here in this proposition, what I've just written is like, for any dimension, if you take a Bernoulli P random for an appropriate P, in this case, P is going to be equal to H inverse of S. If you take a Bernoulli P random with appropriate P, then you'll have a real whose dimension is equal to S, but that you're going to need to use at least this density of changes in order to bring it up to density 1. So then you can ask, like, is this good enough? Like, can you always do it within this distance? And so the third theorem says, like, yes, this distance that is the sort of like worst case bound that you get by considering having to come up from Bernoulli P random is distance that will always work. All right, so before I get into proving this, I just want to, again, like draw a few pictures and try to give a sense for like what's the right way to think about these facts. So all right, so the first result said that if we want to start out with a sequence of effective dimension 1 and change it on as minimal number of bits as possible to reduce it to something of dimension S, then the number of bits, the density of changes that we're going to need to make is this function H inverse of 1 minus S. On the other hand, if we start out with something that has dimension S and we want to put it up to dimension 1, then we may need, but it will suffice to use distance 1/2 minus H inverse of S. So in general, some greater distance. So one way that you can think about this is going back to this relationship between density and dimension. If I try to draw on here a sort of like a mass graph, so think of this as some kind of like way of indicating how many strings there are of each density. So there's like not very many strings of a small density, but there's like a whole lot of strings of density 1/2. This is actually probably should be even like steeper, but I can only draw it like so well. So if you want to start with something that is random, so you're definitely starting with something that's like pretty close to the center here, and change it down to something that has dimension S, well, if you look at strings of length n, then there are 2 to the n many strings sort of like represented in this hump. But if you look at strings that just have effective dimension S, then there are 2 Sn many of them. But they actually are pretty evenly distributed because, for example, you could say, all right, I'm going to come up with a set that has an effectively describable like short description set that has size to the Sn by just saying, give me to the Sn points sort of evenly distributed throughout this space. Right? So every one of these 2 to the Sn points is in like an easily describable set of size 2 to the Sn. So each one of these points is going to have dimension less than S. And because they're pretty evenly distributed, if you start out with something that is random, then you're not going to have to go very far. So corresponding to this H inverse 1 minus S in order to find a dimension S. On the other hand, if you start out with some string that has dimension S, but maybe the reason it has dimension S is because it has a really small density, then yeah, you're going to have to travel probably a pretty big distance in order to get to a random just for the density reasons. Okay, so that's our universe. So now let's look at the method used for proving theorem 3. So used for proving that this 1/2 minus H inverse S distance will be enough. So there is a finite fact. There's a fact about finite strings that basically says if you want to do this same thing for finite strings, then you can do it. So there's in all of these finite facts, I'm sort of eliding some kind of like epsilon goop. So there should probably be something like, for every epsilon, there's an n, such as for strings as long as n, then like these facts will be true to within epsilon. But this is sort of the core idea of them. So we want to take this finite fact and lift it to the infinite situation. And we kind of want to do it by something like what happened for that first example, where you just like divide it into chunks and just like do the finite thing on every chunk. But it's not quite so easy when you're increasing information, because basically, so going back, where'd it go? Yeah, so basically if you have this x and you're trying to like make this y sort of piece by piece, you say, okay, I started out with sigma, now I'm going to replace it with a tau where tau has more information. Here I start with a sigma that's maybe approximately s, now I'm going to replace it with a tau that has dimension 1. So you're like trying to add more information here. The problem is that x can kind of copy the more information that you put and like make your job harder, so you have to put like even more and even more. So you can't really quite do it in a greedy fashion. But you can basically still accomplish the thing that you want to accomplish with respect to changing that initial x chunk by chunk. And the way that we will black box it for the purposes of this talk is just to put it inside this main lemma, which I'm not going to prove. But this lemma says, okay, so suppose that you have this x where you've divided it into chunks of the appropriate rate. And recall that we're always going to use SI to refer to the conditional dimension of the ith chunk. Now, the lemma says, suppose that you specify a bunch of t's. So the intention here is for these t's to try to be the conditional dimensions for the chunks of y. And also specify a bunch of d's, with the intention being that these are supposed to specify the density of changes that you need to do to go between the two chunks. As long as you specify those t's and d's in the right way, so this is the right way, then there will be a y with the property that the conditional dimensions of each of these taus are greater than each t, and also that the density of symmetric differences between each sigma and tau is less than the d's that you chose. So notice that if the ti are equal to 1, then we're looking at h inverse of 1. So we're looking at 1/2. So that gives us that 1/2 minus h inverse s in the case when t is equal to 1. But the finite fact about starting out with an arbitrary sigma that has dimension s and increasing it to dimension t is that in general the distance that you need is h inverse t minus h inverse s. So this is for exactly the same reason why it took so much dimension to bring a Bernoulli p random up to dimension 1. Now if you just want to bring it up to dimension t, this equation again describes just the pure amount of like density difference that you're going to need. All right, so this relationship describing the optimal distance that is always sufficient for raising a finite string of dimension Si to a finite string of dimension Ti is going to feature in the rest of everything that I say. All right, but this lemma says that if you pick some like sort of desired way of setting your goal for what you want the dimensions of each of the y to be and what you want the distances to be, then as long as it's possible, you can do it. And of course, you can look at the SI when deciding what you want these T's and D's to be. All right, so now let's prove the theorem 3 using that main lemma. So this proof is a convexity argument. And the important part of what's written there is to say we're going to set all of the T's equal to 1. So we're going to say we want to start out with something that has dimension s, this x that has dimension s. We want to raise it up to have dimension 1, and we're just going to do that by making every chunk of y have dimension 1. And we're just going to do that with whatever d the formula says will be enough. Right? So if x gives us some sigma that happens to have a small effective dimension, then we're going to use a big D to bring it up to 1. And if it gives us a pretty good effective dimension, we're just going to use a small d to bring it up to 1. So just drawing again this curve that we're using, this 1/2 minus h inverse of s, you can see that what's happening is that the opponent basically gives us these chunks, S1, S2, S3, right? They appear at various locations. So this is conditional dimension for the initial segments of X. And then here are the densities di that we're going to get changed to. All right, so that means that for each one of these, this is the function that tells us, all right, for this first chunk I had to use this distance, for the second chunk I had to use this distance, all right, and so on. Now, at any given time, the effective dimension of some initial segment of X is some convex combination of these things. So it's like something, let's say, so like S is the thing that it's ultimately headed for in the lim inf. So like maybe some running average, like got close to S at some point. Well, that means that also the running density average that we've used, because of the fact that this function is convex, has to lie below it somewhere. Okay, so as the as the running averages of these conditional dimensions move around here, the running averages of our densities move around under here. So it's exactly the convexity of this function that allows us to conclude that the density is going to be smaller than the target density that we're going for. Because if this S is finally the effective dimension of X, then this value here is the maximum density of difference that we're allowed to use, and we're always staying below it. Now, that X has effective dimension S, so it's not a limit, it's just a lim inf. So infinitely often, the running averages may end up over here. But that's also okay, because they're still going to be lying below this function, and this function is decreasing. So we'll still be within the required density, even at the points in time when the momentary dimension of X has risen above S, as it may do infinitely many times. Okay, so that's it. Like the main lemma did some work to say that we could make a y that like had this property where all of the initial segments have effective dimension 1, and then we use this convexity argument to show that the densities have to be below this line. Okay, so those were the two preparation examples. So summary of what we did, said if you want to start out with dimension S and increase it to dimension 1, so in the next slide, so things that are in blue are going to change in the next slide. So if you start out with something of dimension s, raise it to dimension 1, then you might need at least distance 1/2 minus h inverse s to do that, and that distance is enough by that convexity-based construction. And if you want to decrease the dimension from 1 to dimension s, just for like information coding reasons, you're going to need at least h inverse 1 minus s, but this distance is also sufficient. Okay, so now what happens if instead of saying we want to go back and forth between dimension s and randoms, we say we want to go back and forth between dimension s and just some dimension t, where t is greater than s, but possibly less than 1. What breaks? Well, first of all, what changes do we want to make? So if we're only going up to dimension t, then the optimal distance now becomes h inverse t minus h inverse s instead of 1/2. And if we are decreasing from dimension t to dimension s, then the same information coding argument shows that this is sort of the naive bound on the distance. But both of the constructions break. And they break for different reasons. So this, the construction that I showed you second, but which I'm going to continue talking about now, which is why it's written first here, this convexity argument is going to break. From decreasing from dimension t to dimension s, it's going to break even worse. And I'm actually not going to talk more, I'm not going to talk really more about this case much in this talk because it breaks so badly, even for finite strings. And the reason for that has to do with a possibility for redundant coding of information in a finite string that has effective dimension less than 1. All right, but let's look at this argument that we had and what breaks about the convexity when we try to raise to dimension t instead of trying to just like raise fully to dimension 1. Okay, so if you look at the strategy that we used in the first case, which was basically set all of the ti equal to 1 so that all of the segments have high dimension 1. That strategy could be described as use whatever distance is necessary, use whatever density of changes is necessary in order to pump up each individual chunk to the desired effective dimension. So kind of the analog of that in the fixed t case would be whatever dimension of chunk the opponent gives you, you raise it using whatever distance is needed to get to dimension t. So for example, if they just gave you like something empty, then you would have to use h inverse t much density of information in order to get you'd have to use h inverse t much density of bits in order to get t much density of information. And in general, that function, h inverse t minus h inverse si, describes how much density of changes you would want to make for any given si that the opponent might care to throw at you. Now, that works all well and good when the opponent starts giving you si over here. It's very clear what to do. But this strategy, just as printed right here, is incoherent in the case when the opponent tries to give you some chunk that actually already has dimension greater than t. Right? So t will be the point where it crosses 0 here. So in that case, this graph, although it is concave, is basically telling you, all right, use a negative distance between the sigma that was given and the tau that you're trying to find. Use a negative distance between those two in order to decrease the high dimension of sigma down to just t. Okay, so that's nonsense. We can't use any like negative distance. So the best that we could do in case the opponent gave us a chunk that just already happened to be pretty complex is just like leave well enough alone. Okay? So don't change it. All right, well, that obviously creates a problem because that means then that the strategy that we're following is not convex. So this is the sort of description of the distance strategy. And so, of course, the opponent then can mess with you by putting like some, S1 chunk here, put S2 here, S3 here, and so on, back and forth, so that it's ultimately sort of aiming for this effective dimension S, but forcing you to use this distance and this distance again and again for a total average distance of too much. All right, so this same strategy that we used to raise completely up to a random won't work when we're just trying to raise up to dimension t. The opponent can mess with us using the lack of convexity. There's another strategy that you might immediately think of, which would be the strategy of instead of raising each chunk immediately up to t, just say, okay, here, this d, h inverse t minus h inverse s, is like the total amount of distance that I'm like ever allowed to use. So how about I just use that distance on every chunk and just increase the dimension as much as I can within that distance and hope that it's enough. Okay, well, if you do that, so just so in the main lemma, just setting all the di's equal to d, and then like set the t's be TIs just like however high you can get them, subject to the fact that you're changing by d. Then you get some kind of gross function, which I don't necessarily recommend looking at, but if you graph it numerically, then you can look at it, which is what we did. And it looks like this. So if you get input of the opponent has given you SI, then you're going to output dimension TI. If they gave you basically nothing, then by using h of that fixed distance, that's like the most information that you can get in. If they give you everything, then you don't want to change anything. And in fact, within a fixed distance, you can get up to one, just like full stop. You can just get there. And then in between, the graph of TIs that you'd be able to get looks something like this. All right, so the most important thing to notice about this graph is that it's neither convex nor concave, which is already sort of a hint that it's probably not what we were hoping for. So because of the fact that this graph is showing us the dimensions of the chunks of y, the thing that we were hoping for was convex or concave up. Because it's OK to make y have an even larger effective dimension than t. Like you can always just sort of do a little fewer changes and get it down to t. But if the dimension ends up being less than t, then that's the situation that we don't want. And the problem is that when the opponent puts their SIs wherever it places them, if we follow this strategy, then the dimensions of initial segments of y are just going to be within the convex envelope of this function. So they'll be anywhere from in this region and this region. So anywhere in here is where the values for the effective dimensions for initial segments of y can be. And so you see that if S is actually kind of big, then we can very easily end up with a y whose effective dimension is too small. If S is small, then maybe this could work, but clearly it doesn't work for all pairs of S and T. Okay, so that's the convexity problem. However, the desired theorem, the desired generalization, all right, so I'm calling it theorem 3 plus because it was theorem 3 that was just the special case we saw earlier when t was equal to 1. So theorem 3 plus, the generalization for any s less than t less than or equal to 1, is that it is true. Okay, so if you have any x with dimension s, then you can, within this density of changes, find a y with the dimension of y is equal to t. And the proof uses the following strategy. So this is a strategy that says, given the SI, it'll tell you what to do with the t. So whatever the s and t are that you're initially given with, just like put it, plot that in the box. All right, so this is going to be, what should we do? What should the ti be given the ts? And also consider the point 1, 1, and draw a line between them. All right. Now, the rule is whenever the opponent gives you the SI, you just pick whatever TI is needed in order to stay on this line. All right, so if you do this, then you will definitely end up with a Y that has an effective dimension that's large enough. Because it will always be the case as the running averages. So let's say, yeah, so here's S. So as the running averages for the complexity of X dance around in this area, the running averages for the complexity of Y will dance around on this line. So sometimes they'll get down to being equal T, sometimes they'll be above it, but above is okay because more complexity is okay. So this will give me a Y that has the right properties for complexity. So the only thing that we need to show is that the density of the difference is okay. So we need to say, okay, this is what I want to do with the t's. What do the d's have to be in order to do this? And will that give me a small enough distance? So I didn't even write down the formula that says, like, what is d in terms of t for this strategy, because I don't think that it's very informative. But we graphed it numerically, and what we found was something that looks like this. Oops. Okay, so this whole thing, this pair of facts is what I'm calling the line towing strategy. So you're sticking on this line. So when you graph the density of changes that you need, it ends up looking something like this, where every one of these densities would be appropriate for, so like if this is S, then this is the target density for S. So there's a fixed T that's sort of implicit in this graph. So what this graph is saying is that in the context of S is fixed, where the sequence of dimension S is like given to us, so S is fixed. The T that we're trying to get to is fixed. This graph shows, given a chunk of dimension Si, what is the density di of changes needed just for that chunk in order to get the corresponding y chunk to get up to Ti. And when we look at this graph, we see a great thing, which is that it's concave down. And so again, so the reason that's a great thing is because these, it's going to be, the running averages are going to be like dancing around down here. We're going to be using some densities here, but the running average of densities that we use is always going to be below this line, and this line represents the acceptable densities to use. So the fact that it's concave down is a source of great enjoyment. Unfortunately, it was just a numerical simulation. So at this point, I want to take a little pause and tell a story about what was happening in the world at the time that we were working on this stuff. So last fall, I was visiting the Madison area, and I gave a talk that was basically talking about the stuff that I mostly skipped in this talk, so the earlier results, and mentioning this increasing dimension S to dimension T as an open question in that talk. But Joe was in the audience, who was one of the co-authors for the first part of the work, and he was like, "Come on, we can figure it out." So this line towing strategy came from Joe, and so we were working on it. I was in Madison in the fall, which means during the semester. Okay, so I had taken some time away from teaching. I was teaching calculus. I had a substitute teaching my calculus class. And it just so happened that the material that that substitute was supposed to be teaching them was concavity, the second derivative test, like showing that a function is concave. And as it happened, the substitute did a terrible job. Like, the students, like, you know, I came back and it was like, you know, telling whether a function concave, it's like impossible. It's like, you know, you can't even do it. Like, he just explained it in such a way that they were completely confused. And so I thought that, in hindsight, that there was really some poetic justice that while my students, you know, in my absence at UConn were struggling to show that some simple function is concave down under the instruction of a poor substitute, Joe and I were in Madison struggling to prove that this function is concave down, which of course is not a polynomial. It's like it has logarithms and, you know, something like that. We had to learn Mathematica in order to do it, actually. We were doing it by hand and just like dropping signs everywhere. It was like a mess. Like it wasn't going to be anything. So, so eventually we did it. 7 derivatives later, including 1 partial derivative with respect to one of the parameters. But it's true. It's concave down. Okay, so, you know, we rejoiced. We're done, right? Well, not quite. Do you remember over here, when we were doing this more simple argument, I mentioned the point that even though the effective dimension of x is eventually going to be s, that's just a limit. So infinitely often, in fact, the running average of dimensions can end up over here. So infinitely often, the running average of the densities can end up somewhere like under this part of the graph instead of under that part of the graph. But it's fine to be under this part of the graph because the function is decreasing. So being under this part of the graph means that you are still within the distance that you wanted to use. This function has places where it's decreasing, but those places are not everywhere. Right? So in particular, for some small s, if this very small s down here were actually the s that x was aiming for, then by following this strategy, we could, every time the dimension, every time the running average of conditional dimensions gets pretty close to s, then we would end up with a distance that is precisely acceptable, like or less than that. But infinitely often, the running averages could come up here, and then we might end up having to infinitely often use some distance like this, and that distance would be too much. And using that infinitely often, because our distance is measured as lim sup, is bad. We can't do it. So actually, you know, as excited as we were about the concave down of this function, this actually isn't a complete strategy for solving this problem either. All right, so at this point, you may remember, where did I put this? All right, so at this point, you may remember that we actually, so this strategy, okay, so this is for a fixed t. So I've just drawn one example for one t, right? But when you draw different examples for different t, it looks kind of similar. Except some like very large t, actually, it'll be completely decreasing if t is like big enough. But for most t, you have some small s's where there's a problem. And we actually had a strategy that seemed to maybe do okay for small s's. That was this strategy, the constant distance strategy. So I said, okay, let's revisit that. Before we okay, yeah, so this is what I was just talking about, but I wanted to even give one more detail about it, which was to give you a formula, which I really am only putting up there in order to convince you that it's a little weird, and a picture of what are the values, the pairs ST, for which this line towing strategy works. So this triangle is supposed to represent all the possible values of S and T. We're only caring about values where T is greater than or equal to S, so that's why it's a triangle. And so we figured out, like using some calculus, take some derivatives, blah, 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 that the pairs S and T for which that line towing strategy works are exactly the pairs S and T that satisfy this weird inequality. And if you graph those, then they are here. right? So here, this is like the line towing region of line towing effectiveness. Right, so we sort of partially solved the problem. For some pairs of S and T, this strategy is going to work. So then we sort of started going, okay, at this point we really just want to be done, right? So we said, okay, let's just look at all the other strategies we have, see for what pairs of S and T do those strategies work, and hopefully we can just cover this whole space somehow. So we went back to the constant use a constant distance strategy. So that was this one. So the strategy that just always used the constant acceptable distance. All right, because that one seemed to succeed for some small values of S. Okay, and great news. So I won't go into details, but these small values of S where this function was convex. There really are some values of S down here where this strategy works. Reason roughly being because if you are trying to get to, let's say here, so this is sort of the target complexity that you want. Even though all of the complexities of your running averages in general could end up in this entire red region, that's okay because the function is convex up here. And then this whole region where the function is not convex up, it's still the case that the convex envelope of that function still gives you complexities that are bigger than the complexity that you needed. So it does work for some S, and for some pairs of S and T, because of course there's some constant distance D here, so there's some constant T that's like sort of implied in this situation. And if you then go through the calculus and calculate, okay, exactly for which pairs of S and T does this strategy work, you get something that really surprised us. The pairs S and T for which the constant distance strategy works are exactly the ones that are satisfying this equation. So I did that, so that's not a copy error in the slides, okay? The line towing strategy works at ST if and only if this weird inequality is satisfied with the less than sign going in this direction. And the constant distance strategy works for pair ST if and only if S and T satisfy the same weird inequality with the less than or equal sign going in the other direction. All right? So the pairs ST for which the constant distance strategy works are exactly these. Right? And on this separating line, both strategies work. But deviate from the line, and only one strategy will work. Huh? That's what we said. Like, what's going on here? So anyway, our hope was filled out. We managed to cover the space with working strategies. So modulo a lot of hand waving. I've proved to you Theorem 3+ now. But it sort of leaves us actually with kind of a question, which is basically, what's going on? Like, these two strategies seem kind of a bit ad hoc, I guess you could say. So the fact that they like dovetail with each other exactly, it couldn't be a coincidence. So I'd like to know, like, what's happening? Like, you can. So this weird inequality, it's related to the slope of this line. And it's also related to the slope of the line that connects 1, 1, like to the point on this function where it'll be tangent. So for pairs ST that actually like lie on this boundary, if ST lies on this boundary, then the reason that either strategy works is basically because like this line could sort of be like, it's the same as like this line. All right, that's the best I can do though. I don't really have a satisfying explanation for why that happened. Okay, so let's wrap up the talk. So what did we do? We've just talked about increasing dimension S to dimension T based on going from randoms that have trying to go from randoms that have this density, Bernoulli randoms that have this density, to Bernoulli randoms that have this density, we know we're going to need at least this distance. That part was unchanged from the beginning. But this new construction with 2 cases shows that this distance now also suffices for the infinite increasing dimension from S to t less than 1 case. And then here I've just copied what we don't know about decreasing dimensions. And I just wanted to make one more comment about decreasing the dimension, which is that, in fact, this distance, which, so this construction that we saw at the very beginning broke because the finite version of the theorem wasn't true. And the finite version of the theorem fails so badly that you can make an infinite example that also fails so badly. So this is definitely not the distance that you need in order to decrease information in general. In general, the distance you need is more, but I don't know how much more. And I think that knowing how much more would require probably understanding more of the Vereshchagin-Vitani theory than I understand. So I'll leave up the 2 questions of the talk, namely that one that I just mentioned, which is if you want to decrease dimension, in general, what distance do you need? And then, yeah, what's going on with this division of the space into 2 ad hoc strategies that actually match each other perfectly. So that's the talk.
Any questions? Which version of dimension did you use? Sorry, I didn't get it.
Say again?
How's local?
Effective dimension.
Which is lim sub.
Inf. Oh, I'm sorry. I probably should have said that at the beginning. Yes. For the packing dimension. Yeah. So I think that probably none of the arguments that depend on none. No, maybe some. Okay. So the difference between using the packing and the Hausdorff dimensions is whether or not the running averages are infinitely often going to be just bumping up here to the right of the target, or whether they're infinitely often going to be bumping down to the left of the target. So if you want to use packing dimension, then wherever I wanted a function to be decreasing, I would now want it to be increasing, but I would still want it to be concave down or concave up accordingly. But I don't know what exactly the results would be, but that would be the kind of changes you'd have to think about. Say again?
The naive bound that you had before.
Well,
These functions H, these are all.
so the naive bounds are all. Let's see. There you go.
I would expect some sort of duality. So I would expect that the situation is the other way around. The case is changed.
Yeah. I think
You really can't control both.
Yeah,
Increasing and decreasing the dimension.
Yeah, the problem is you can start back in dimension 1 and have lots of, you can change an enormous number of things to 0, but then so I don't know.
Yeah. Okay, yeah, maybe.
Because you only have to go up every so often.
Yeah.
Right.
Just lay around like a fish.
Yeah, but somehow the cases in which you decrease and increase the dimension is to an inverse to the other case.
But you can change upper density 1 many bits and stuff back in dimension 1. Right. That's the problem.
Well, so the fact that we measure the density of symmetric, the fact that we measure the distance between 2 reals by using the upper density is also another factor that you could consider changing. So if you
Make a lot more sense to just assume that, but even there.
Any relation to the dimension of sex to Hausdorff disintegration distance?
Yeah, the classical question.
I just have notes.
yeah, I'm not sure.
Yeah, of course, if you have things at distance 0, they have the same dimension. But if you take some sort of supreme line, it's interesting to see the
But Haus's theorem is a classical fact, so maybe that would have been.
So I didn't really talk about it. So in order to prove this theorem, you use some arguments similar to the arguments for the main lemma, but because you're trying to change to get into a Martin-Loaf random sequence, it's no longer enough to just like do something chunk by chunk, because those this approximation thing definitely like loses some bits, and with a random you can't lose any bits. So for this one, what you have to do instead is say that you're going to still be sort of like changing x chunk by chunk, but now when you do those changes, you can't just change to any old chunk's tau. You always have to change, like, all right, so I mentioned at the beginning that even for the main lemma that I stated, in general, you can't do it greedily. And in this case, you can't do it greedily either, but you can prove a lemma that basically says that as long as you managed, while keeping the dimension of y, as long as you managed to find some y that had an appropriately high dimension while being like within a small distance from x, then when you consider the next chunk of x, you can always find some other like very good, so like initial segment of a path through a tree of randoms. You can also find some very good tau that may be like different from the one that you had, but you just like switch, say, okay, now I'm doing this like completely different string. But a compactness argument then allows you to eventually like find a path through what you did.
So you gotta change your mind.
Yeah.